Saved by the bell. Okay. So next we have David Lin from San Diego. Tell us about locally testable codes.
Yeah. Hi. So I'm David, and today I'm going to talk about a kind of code that's very related to PCP, and so which is this quantum locally testable code. So in this work, we construct a new family of quantum locally testable codes, which has like nearly optimal distance, so nearly optimal up to like polylogs. And this work is done with Irit and Thomas. Okay, so we'll quickly review quantum codes. So quantum codes are defined by two parity check matrices, Hx and Hz, and they satisfy this equality. So Hx transpose times Hz is equals to 0. So that's the standard definition for quantum CSS. But often it's useful to rewrite it into this form. So here we have three vector spaces, and then these two linear maps. That comes from Hx and Hz. And this condition below is exactly saying that when you compose these two maps, it becomes 0. And there's a fancy name for this, which is called chain complex. So later on, if you see like these linear maps, they always have this property. Like when you compose twice, it's 0. OK. And for this talk, we'll care about these 5 parameters. So n, k, d, w, and s. So n, k, d are fairly standard. So they're the number of physical qubits, the number of logical qubits, and the number of polyflips that change from one cohort to the other. And w here is the locality, which is the maximum Hamming weight for all the columns and row in Hx and Hz. So equivalently, it's saying that Hx and Hz, they're sort of sparse matrices where w is the weight. And when this w is constant, these are also referred to as the LDPC codes, which will also appear later. OK, so that explains the first 4 parameters. But there's the last one, this s. And that's exactly the one that characterizes local testability. So to motivate the definition, we'll ask, OK, how do we know? So given a bit string, how do we know if it's a code word? Well, one way is to just multiply by the full parity check matrix. So by definition, the result is 0 if and only if the bit string is a code word. But now you might ask, OK, maybe it's enough to just pick a random check. So we just pick a random check, and then we just test if when you multiply 2, if it's 0 or not. And this test is particularly nice because when your parity check matrix is sparse, this actually gives you a local test. So what I mean is that if this check, so when the matrix is sparse, this check only contains constantly many 1s. And so that means to test that parity check, all you need to know is like Ci, Cj, Ck, like just 3 bits from the string. So that's why it's called a local test. And the condition for being a locally testable code is exactly saying that, OK, this local test, the second one, is almost as good as the global test. And this can be summarized into this inequality. So on the left is the local one, and on the right is the global one. So here, HZC is the number of failed checks. This cur HZ is the code word. So this, So this distance, so this DC cur HZ is the distance of C from the closest code. Here, MZ and N, they're just normalization factors. And finally, this S is the soundness parameter. So whenever your HC satisfies this kind of inequality, we say that this matrix has like local testability. And for quantum codes, we want both Hx and Hz to have this property. So the quantum soundness would be the minimum among the two. Like MZ and N? So it's like, so HC is the number of failed checks, but the way you test these things is you just randomly sample a check. So that means you ask like, what's the probability of the check failing, and so you have to normalize it. HDC, yes, it's you take the weight. The weight is exactly the syndrome, and so that's the number of failed checks.
You're not assuming the checks are independent.
That would be very important. So that would come up multiple times later. Yeah. So yeah, indeed. So later on, these checks won't be independent. Okay, good. So yep. So here comes the main results. So the main results of the paper is that assuming the existence of some codes, which I will say more later, then there exists a quantum locally testable codes with these parameters where everything is optimal up to a polylog. Okay, so here currently this theorem is conditioned, but in fact there is a paper in preparation which proved the existence of such code, and so together that gives you an unconditional explicit construction of almost good quantum LTCs. And for some applications, you might want to have constant soundness. And in fact, you can also just use standard amplification technique, like similar to parallel repetition. And now you can get constant soundness at the cost of the weight.
Okay. Previous slide was defined as unnormalized, right? But we really mean divided by N.
Yeah, they're normalized. S here are. So, okay.
No, here you put S by N. So
That N is normalizing the distance.
Yeah, N is normalizing the distance.
Oh, okay.
Right. Yeah, because sometimes there are notation that means relative distance. Yeah, okay, good. So, okay. All right, so that's the results. Yeah, but if it's the first time you see this definition of locally testable code, you might wonder, like, okay, why is it interesting? Like, why do we care about these codes? And so I'll explain like why we care about them. So one reason is that, well, these things are like robust objects with a kind of local to global property. So more explicitly, what I mean is that when you have a word that's locally approximate a code word, then this condition is saying that, okay, it's actually globally approximate code word. And even more explicitly, what I mean by this local and global exactly correspond to the two sides of this inequality. And for this robustness, what I mean is that for the non-robust version, it corresponds to this property, which is that, okay, if the syndrome has weight 0, then it's exactly a code word. So it's a bit tautological because, well, that's exactly what code words is about.
Here approximates the different motions. One is approximates in terms of energy, one is in terms of direction.
So here approximates. Okay, so for the non-robust version, you can sort of like replace approximate with the word is. So if C is locally a code word, which means it passes all the checks, then C is globally a code word, like it's actually a code word.
So that's true in general.
Yeah, it's true in general. It's true in general.
Robust version of that.
Yeah, I just want to clarify what I mean when I say robust, the word robust. Yeah. But again, you might ask, okay, why do we care about these properties? And the reason is that these robustness is exactly the essence of like quantum PCP. So PCP is roughly saying that when there's an algorithm that converts a proof into a kind of robust proof. However, at this moment, we don't have quantum PCP. So that means, well, we don't know a robust object yet. And so that's what makes these quantum locally testable codes interesting, because they're sort of the frontier of these like robust objects. Okay, so that's why we care about these codes. And now we'll go into some history, like what do we know about them? So to understand these quantum locally testable codes, it's often helpful to know about their like siblings, which includes these classical LDPC codes, quantum LDPC codes, and the classical locally testable codes. So the thing that connects them all is this chain complex condition. So just to remind you again, chain complex is just a bunch of linear maps that compose to 0. Here, for the first two, like these locally, like these LDPC code, the relation between the code and these linear maps are fairly straightforward. It's simply the parity check matrices. But for the classical LTCs, there is this additional map which characterizes the relation between checks. Yeah, and as mentioned by the audience, like this is actually a very key property for these locally testable codes, and we'll explain more on that, like why they appear later. For now, I just want to say that these quantum LTCs, they're really like an extension of these constructions on quantum LDPC and classical LTC and into like a longer chain complex. So let's sort of review these recent works. So for these LDPC codes, classical LDPC codes, they're constructed by like Zipser and Shulman, like these expander codes, and these are the Tanner codes built on a one-dimensional graph. The recent breakthroughs on quantum LDPC and classical LTCs, they're Tanner codes built on like two-dimensional square complexes. And for us, we are doing a similar construction, but now in a four-dimensional cubical complex. And so that's what we'll explain more later. Here, I just want to highlight that a lot of our proof techniques actually borrows from these works on DHLV, which borrows some like inspiration from this DLM. So that's a paper that constructed the like the C3 locally testable code. So these are the work after sort of the breakthrough on quantum LDPC, but before that, people have also studied these locally testable codes. So here are the two main papers, and here we can see the main difference is that previously the distance is bounded by the square root barrier, but here we can improve it all the way to optimal up to polylock. Also, we also improved this dimension. So originally it's constant, but now it's optimal. So that's the main difference.
So before your work was rate 1 and distance n was when was it?
Like rate 1, like was there work that achieved rate 1?
Yeah.
I think no.
Just got everything right.
Yes, yes. I should also say that in general, people care more about like soundness, like parameter of soundness, and also distance, because that's a more like that seems to be the more challenging one. So maybe these works can indeed be turned into a constant rate, although I don't know, but it's possible. Okay. All right. So now we'll go into. Oh, actually, okay. So now I will come back to this question, like about the relation between checks. Like, why do we need them? In fact, there's a very simple reason. So if there's no relation, then actually the parameter would be very bad. So let me just explain why that happens. So when these checks are independent, this parity check matrix, this H, would be surjective. So what I mean is that for every syndrome V, it's mapped by something. So what that means is that now I can pick a word C to be the pre-image of this 1, 0, 0, 0 vector. And so if we plug into this inequality, what we see is that the left-hand side is simply 1 over m. And what about the right-hand side? I claim that this distance between C and the code word is of the order d. And so if we plug it in, we see that S would be of order 1 over d. And in the optimal case, this d should be of order n. So we see that this S is 1 over n, which is very bad.
So are you saying here that if you remove one check, you create something that's far from all the...
Oh, I see. You're saying like why? What's the intuition behind?
Yeah. Is it a vision?
So later I will say that you can make this argument rigorous, although I won't. Like, yeah, we can do it. We can talk about it offline. But pictorially, what happens is that is like this. So the x-axis is like the space of bit strings, and the y-axis is like the weight of HC. So this green dot is a code word, and this red dot is like what we just constructed. So here, there are some, in the ideal case, these values touches the bottom, but now there are also these extra values that almost touch the bottom, but doesn't quite touch the bottom. And these are the like the bad instance.
Is the fact that it's 1, 0, 0, 0, 0 important?
Yes.
I guess so, right? Because
Yes.
I can, if I take a surface code and delete 2 checks and make a code word that's sort of very close. Schwartz strings. Or maybe I'm misunderstanding this.
Okay, the reason that this 100 is important is because like that's how we get
The one over M.
this one over
Okay.
Yes.
Then I'm misunderstanding it.
So
Are you just saying there's strings that violate one parity check and only one parity check?
yes, exactly.
And to be in the code, they therefore have to have distance, or is it maybe not to be in the code?
Yeah, this part is not that obvious, right?
Yeah.
So that's why I'm not explaining it here. But in any case, we can make these whole argument rigorous. So in fact, we can get this kind of bound, and indeed, it's far from the optimal, like what we hope for.
Oh, sorry, I'm just a bit confused. Follow up to what John said. So, isn't it simply saying that if you are allowed to violate one check, then you can create code words that are far from any other code? And it's like what's that? So you said it's not obvious, but
He's not proved that.
I didn't prove it on the slides, but you can
It's
prove
a
it.
can create. It's not all such things are. Yeah, there is a C in the pre-image that has this property.
Oh, I think it's all C in this pre-image. But it uses some property of the LBPC and
Okay, yeah, so
And
this
I-
is for a specific code. Or
no, this is for all code. So for any code with a relation, you have this.
Okay, maybe I'm misunderstanding the no relation part then. Okay, I'll figure it out.
Okay. So when I say no relation, I mean like all the checks, they're independent. So yeah, there is no redundancy inside the checks.
Sorry, if I just have the code where every parity check is like, I have one for the ith bit, and I just expect it to be 0. And the only code word in there is the all 0 string. Then the string that's 1 in the first bit and all zeros afterwards, it violates a single parity check. But like the code that's all zeros, its distance isn't like it's infinity or something.
Yeah, doesn't that find distance?
So this is an example of one where I violate a single parity check, but like I'm distance 1 from the code rather than being distance infinity.
You probably have to put that one in a random place.
We can talk about it later.
Yeah.
Put the one anywhere.
Yeah. So and if you put it in a random place, probably it will get around John's.
Okay, yeah, we can talk about that later. Yeah. So yeah, in any case, that intuition sort of works out. And okay, and what happens when there are relations is that this H is no longer surjective. So the previous construction doesn't really work. So meaning that there might be no pre-image for this 1000 vector. And so now the picture becomes something that looks like this. So the image only covers some part of the vector. And so we have this very nice phenomenon where all the value indeed touches the bottom. And in fact, if you look at all the famous locally testable codes like Walsh Hadamard, Reed Solomon, Reed Muller, they all have these relations. So it's a really good exercise you can do afterwards. So that answers the relation. And so now we'll move on to the construction. So to the overview of the construction. So for all these codes that I talked about, they
Sorry.
yeah.
For the Hadamard code, can you just like quickly say what are the relations there? Is that obvious or is it not obvious?
It is obvious. Yeah, I can do it. On
Is it just like two of them should sum to two of the relations sum to make another relation, and that's
right.
okay,
So
I'm happy with that.
okay.
and for repetition code, it will be all cycles.
Like for repetition code.
So I'm gonna create a graph.
Yeah, so these are slightly, like these definitions are slightly subtle because now to define a code, one cannot just specify a vector space, one also has to specify the parity check index. And so indeed, if we take a type of parity check, like we make sure that all bits are the same, then indeed what we say is correct. Okay, so for the construction, yeah, so all constructions all follow this similar general scheme, which is that we will combine a graph and then a code, a local code, to form like the Tanner code. So in the simplest case of expander codes, we would take this spectral expander graph and then a local code with large distance. So lambda here is the spectral parameter and d is the distance. And again, in this context, they're both normalized. So meaning that this lambda is divided by the degree of the graph, and this d is divided by the length of the local the thing that relates these two objects is that the graph degree is same as the code length, and which denoted as this delta. As a side remark, these graph often comes from these Cayley graph, and this would appear again later on. Okay, so now I say there's this general construction, but in fact, it's not the case that all construction has nice properties. So when do we know this works? And fortunately, there's a simple criteria. So when the distance of the code is larger than lambda, then together you will get a good expanding code. And now can we achieve this parameter? Yes. So you can take this Ramanujan graph where lambda is of order 1/square root. And you can just take a random code where d is linear to the length. So that's constant after normalization. So that's the construction for expander code. You pretty much do the same thing for these quantum codes, for quantum PC codes. So now you have to move one dimension higher, so we are doing a two-dimensional construction. So here we take this left-right Cayley complex, which have this two-dimensional structure. And for the code, to reflect this two-dimensional structure, we actually have to take two codes, so CA and CB. And in this context, we now have also two kind of distance. So D1 is the usual distance, but there's also this D2, which is about this robust property that sort of appeared in the theorem statements. Yeah. Also, these Cayley complex also has different names. So these are also sometimes called these 2D square complex, and they can also be constructed using like lifted product or a balanced product. Okay, and again, we can ask again the question like, what's the condition that ensure the combination is nice? And in this paper, DHLV, we showed that as long as this inequality holds, then you will have a nice code. And again, can we satisfy this inequality? And the answer is yes again. We can take the Ramanujan graph, again with the random code. So now you can guess. So in 4-dimension, we follow the same scheme. So now we have to take a 4-dimensional complex, and we have to take a 4D code. Now we have to take for such code with 4 kind of distance, D1 to D4. And what our work say is that, OK, now you have to satisfy another inequality, but that's all you need. So once that's true, then you'll have some kind of local testable code. And yeah, so now there is this question like, does a random code achieve these constant kind of distance? And that's exactly what Kalachev and Panteleev, they will show in the upcoming work. All right, so that's the overview. Now we'll go into more details. So we'll first talk about this cubical complex. So although our construction is in 4D, we'll mostly just draw diagrams in 3D because it's easier to visualize. So the data that we'll start with is a abelian group G with T sets of generators, so A1 to AT. This cubical complex would contain like vertices, edges, faces, cubes, these high-dimensional objects. So here's a picture of it. So for the vertex set, we have 8 copies of G over here. So that means each vertex is labeled by an element in G, and also like an indicator saying that which copy it's in. For the edge, these horizontal edge will connect G with A1G, where A1 is an element in the generator, capital A1. We'll do the same for the vertical edge, which connects G with A2G. And then for the last direction, we'll connect G with A3G. So that's how you connect all the edges. Okay. And also because the generator has size delta, so each vertex is connected to a delta many horizontal edges. That will sort of be important later on. Yeah, that's exactly what I'm going to say. Yes. So what's very nice about this construction is because of this abelianness. So what abelian gives us is that these edges would also form these faces. So here we see that G is connected to AG1. That means it's, and then we can now go vertically, so it's connected to like A2, A1G. But what's nice is that because A1 and A2 commutes, the other direction also goes to the same point. So these 4 points forms a face. And by the same argument, these 8 points would form a cube, and so on. And this whole thing really relies on having an abelian group. So that's the cubical complex. Now we can use this cubical complex to form a chain complex. So the way you do that is, just to recall, chain complex is, again, you have to first define the vector space and the linear maps. So we'll start with the vector space. So what we'll do is to we'll rely on these geometrical structures. So here, x0, x1, x2, these represent the vertex set, edge set, etc. And the vector space would exactly be f2 to the power of x0. So equivalently, it's saying that we are putting an f2 value on each of these vertex. And same for the edge set, and so on. So that defines the vector space. For the linear maps, we'll rely on the incident structure. So what that means is that if a vertex is in a particular edge, then the corresponding entry in the matrix would be, we'll set it to 1. So it's sort of like the adjacency matrix, but it's more like the incidence matrix in this case. And yep, and you can, so that defines this first map, but you can do it for other maps. And now we can check that if they compose to 0. So the reason they compose to 0 is simply that, okay, whenever we have a point and a square, they always share two edges. And because we are over f2, like these two paths just compose to 0. So this chain complex just follows directly from these geometrical structures. But does this define a code? Well, unfortunately, it doesn't, because if you compute the dimension of the code, this k is 0, meaning that it cannot store any information. And so that's why we need to apply the standard code. And that's the next slide. So the standard, so that's what we do. And then this is also called the sheaf complex. And this process relies on these linear maps. So H1, H2, dot, dot, dot. These are the parity check matrix of the code I was talking about. OK, so what do we do now? So previously, we put this f2 value on each of these vertex. Now instead, we will put like a tensor value on this vertex. So it's f2 to the power of m1 times m2 times m3. So that's represented by this blue tensor. So now the vector space is f2 to the m1 times m2 times m3 to the power of x0. You can repeat the same process for like all the other geometrical structures. So for example, the horizontal edge, now you'll put f2 to the m2 times m3. And so that defines the vector space. For the linear map, we'll apply these, like we'll use these codes, these local codes. So these h1 to ht, they correspond to the t directions, and we'll apply such the map that corresponds to the direction of this geometric relation. So for example, this horizontal edge is like the first direction, so we'll apply this h1 map. If you track this map, what you see is that after the map, you get this delta times m2 times m3 tensor, which looks a bit different. But now we can recall that each vertex is connected to delta many edges. So what we can do is to split this tensor into like these delta layers and then just send it to these delta edges. So in other words, if this edge is the a1th edge, then we'll take the a1th layer of this tensor.
Is it difficult to keep this consistent? Because you're sort of making choices of, you're assigning at each vertex, you're assigning sort of this bit of the code to this edge. Think about you have to do that everywhere, and it has to match.
Exactly. That's indeed a very subtle point. So at the very end, I will talk about some other construction. There's some subtlety that they don't work as exactly for this kind of reason. So yeah, so indeed, for this whole construction to be consistent, there's some, like, one actually have to color these edges. So yeah, and what's nice here is that we can say this edge is colored by this A1 coordinate. And that sort of makes things consistent. Yep. And you can do the same thing for other maps and so on. That also be higher maps. Okay. And within this, okay, good. So that's the construction for a sheaf complex. And if we do this in the 4D case, then we will exactly get a chain complex, and that's the code. And within this very giant code, there's a very useful structure to consider, which is this local chain complex. So this structure consists of all the object that's incident to a particular vertex. So you pick a vertex, and then you look at its local views. Yep. And it's a bit complicated, but it sort of looks like this. And I'll explain some parts of it. So here, this f2 to the m1 times m2 times m3, this is exactly the tensor that's valued on that vertex. And here, this delta times m2 times m3, this is exactly like, previously we split it out, but now we just stack them together again. So that's the thing. And now the map is simply this h1. So that's really just the structure. And then, so the whole chain complex, you can write it very succinctly as h1 tensor h2, blah, blah, blah. And why is this important? It's because this robust property is exactly a property about this local chain complex. And it's very important for the analysis. Okay.
The MIs, how do you choose?
Oh, I see. These are like these are the property of the local code. So mi in this case is the number of parity check for that local code. But in this case, you can just think of it as some linear maps. These m1, you have to choose it carefully to achieve the rate you want. So that's sort of the only place that appears. So if you care about distance, then really this local robust property is the more important one.
But it's not necessarily given, like all the way back in the classical planner code, it's not necessarily given by the degree of the expander. The m's.
Oh, the m's?
Yeah.
Oh
no, that's the delta.
The delta, yeah,
Yes.
delta is the.
Oh, but the m's are different. Okay, now I'm confused. Never mind.
M is like the number of parity check for the local code.
Yeah, fair enough.
Okay, so that's construction one. Yeah, we'll just give a one slide proof. So the proof roughly has two parts. One is to show the distance and soundness property of HZ, and that's sort of related to the chain complex in this direction. And the other one would be to show the distance and soundness property for HX, which turns out is related to the chain complex in the reverse direction. So we just take the transpose of all these linear maps. That also forms a chain complex. Okay, so for the first one, the proof roughly follows from the spectral expansion of the graph and the robust property of the local chain. And that's where this inequality comes from. So the proof is roughly the standard random walk argument with some ingenuity in the choice of the random walk. So that's the idea. For this other direction, now you need a different proof. And the reason is that our chain complex is organized by the structure, like the dimension. So it's vertex, edge, phase, cubes, etc. So when you flip it, now it becomes like 4D, 3D, 2D, 1D, 0D. So now you need a different proof. But fortunately, we can just reduce this case to the previous case and using just simple linear algebra. So that's the proof. And so now I'll conclude.
How different is the proof? Is this proof compared to the DHLE proof?
Yeah, it's the same. It's the same. But to make these things, like in 2D, you can sort of ad hocly define some notations, but in the higher dimensional case, you want to make the notation nice. So that's why we have to introduce all these sheet language. But the proof is the same.
So this comment you made about reducing the HX to XZ, how general is it? Does it use very specific things about your construction?
Yeah, the structure is important. But how important, like how much things that can be changed, I'm not so sure. Yeah, at the same time, this reduction doesn't use any expansion property of the graph or the code. It's only sort of like a chain complex tracing, like you trace the chain complex using that kind of technique. Okay, so the conclusion, our construction, yeah, so just to summarize our construction, it's based on these 4D cubical complex and the 4D tensor code. And we can show that together they gives you these almost good quantum LTCs. For the future direction, a natural one is try to remove these polylog factors, which I'll say more on the next slide. But another important one, which ties back to today's program, which is try to move closer to these quantum PCPs. And for these quantum PCPs, now we want to have like more properties of these codes, like some kind of encoding property or like beyond these clip forwards, things like that. So it's also very worth pursuing. But now let me come back to this polylog. So, so one hope is that, okay, maybe we can follow the general schema. But one issue is that this polylog really comes from this abelian group. So that means you really have to try to do something with non-abelian groups. But, well, for non-abelian groups, now you'll encounter some kind of technical difficulties.
Is this because you have to pick the generating sets to be like logarithmic in size in order for it to be expanded, or what's going on? Because I always thought that abelian Cayley graphs of abelian groups are bad expanders.
Yes. So the polylog here comes from the fact that for an abelian group to have some nice expansion property, one way is that you choose polylog generator, like log number generators. That's one.
That's what I thought.
Yeah, exactly. That's one place that's going to kind of would come up. Right. Yeah. So for the non-abelian group, there's this JL complex that still have this cubical structure, but there's some, like when you try to put the two together, there's some technical issue. Like now it doesn't give you a sheet complex. So that's one approach, but there are also other approaches such as like maybe you can use lossless expanders, or there's also the paper that uses cosec complex plus local codes. Yeah, and so currently it will be interesting to see like which non-abelian construction would like fit together. But in any case, like our proof technique is sort of modular, so it might still be like applicable to these other settings. And that's everything. Thank you.
And we